Okay. I'm just going to forward. Sorry. That's a good start.
ágæta dóttorsefni, góðu gestir, virðulegu andmælendur, distinguished opponents. My name is Magnús Tumi Guðmundsson, and as the president or the head, rather, of the Faculty of Earth Sciences, School of Engineering and Natural Sciences at the University of Iceland, you are very welcome to this ceremony. What will happen here today is a PhD defense. Robert Alexander Askew is going to defend his thesis, Breiðdalur Volcanic System, what came first, the central volcano or the fisher swarm? Robert Askew's supervisor has been Þorvaldur Þórðarson, Professor of Volcanology and Petrology at the University of Iceland. Other members of his PhD committee are Ármann Höskuldsson, scientist at the Institute of Earth Sciences at the University of Iceland, and Philip Gans, professor in the University of California, Santa Barbara. Robert Alexander Askew was born in 1989 in northeast England. He moved to Scotland for university education, completing a master's in earth science from the University of Edinburgh in 2013. He began his PhD studies at the University of Iceland at the end of 2013, and he was with us, but over the last year he has had a position at the Icelandic Institute of Natural History, where he principally works on geological mapping. Robert Askew's studies have been supported by a doctoral grant from the University of Iceland and a teaching assistant fellowship. He also spent some time at the University of Akayama in Japan on a Watanabe fellowship. Opponents at the defense are Professor Valentin Troll and Dr. Brian Bell. Valentin Troll is a professor at Uppsala University in Sweden. He is a well-known expert on igneous petrology and eruptive processes who has worked on volcanoes and eruptions from many parts of the world. Dr. Brian Bell is a lecturer in the School of Geographical and Earth Science at the University of Glasgow. He has extensive knowledge and experience when it comes to research in the Paleogene lavas of the North Atlantic volcanic province, including Scotland, Faroe Islands, and Greenland. The PhD defense begins with the candidate presenting his thesis, followed by examination by the opponents, who will discuss the thesis, ask questions, and the candidate will answer. According to the regulations of the University of Iceland, others who are not opponents can discuss the work of the candidate if they have requested to do so with a 24-hour notice. Nobody has made such a request. But I will allow short questions or comments by the audience following the opponent's questioning. Distinguished opponents, I have explained the proceedings of the defense. The candidate will now present his thesis work, give an overview, and I suggest you take seats here in the audience because it's very testing for the questioning ahead to turn your head 180 degrees. So please, and Rob, you can now, when everybody's ready, you can start your presentation.
Okay, good afternoon everyone. It's nice to see so many people here to watch this. Thank you all for coming, braving the weather out there to come to the main building. Firstly, I want to thank my supervisors and committee, and especially I want to thank the opponents for coming all the way to Iceland to watch this defense. So Magnus is already introduced, but again, the title of my PhD thesis, Breiðdalur volcano, what came first, the central volcano or the fisher swarm? We attempted to answer this question through fieldwork and age dating of the volcanic system in the East Fjords. So first, yep, it works, good. First thing I want to do is acknowledge all of the institutes, the groups and funds which helped out with various parts of this project, especially to the University of Iceland Research Grant Fund. Okay, so in this talk I'll go through obviously a brief introduction into Iceland, Icelandic volcanic systems, and then into the Eastfjords and volcanic systems of the Eastfjords, as well as some background on Breitdala volcanic system itself, as well as looking into then the results of this thesis, which is broken down into 3 main papers and a short 4th paper. And then I'll go through some general conclusions at the end. So, Iceland. Most of you here probably know this generalized geological map of Iceland. You can see the neovolcanic zones, or the active zones, running approximately north-south through Iceland. And these active zones connect up with the mid-Atlantic ridge. The architecture of these zones, or the makeup of these zones, is caused by the interplay of the Iceland mantle plume, which is thought to be roughly in this dashed line here, and this mid-Atlantic ridge. On this map, I've pointed out the axial zones of the northern volcanic zone, eastern and western volcanic zones, where the majority of the spreading takes place. And this spreading is roughly east-west, and that means that these active zones, when they migrate to the peripheries of Iceland, they become inactive. And so in the peripheries, in the east, the west, and the north, we have exposed Miocene to Pliocene volcanics that were once thought to be on these zones. And the recent glaciations and deglaciations has both eroded and then exposed these volcanics. Now, upon each of these zones and belts in Iceland, we have volcanic systems. And a volcanic system in Iceland has either a central volcano, a fissure swarm, or a combination of both. So a central volcano, where present is the focal point of magmatic and volcanic activity. There's rather frequent, geologically frequent eruptions on central volcanoes, which means they build up an edifice that usually stands proud of the landscape. And everyone living here in Iceland probably knows these volcanoes. The fissure swarms, on the other hand, they can either have eruptive fissures or just tectonic fissures where no magma comes up to the surface. And a fissure eruption is typically a large volume, usually over 1 kilometer cubed, and some recent fissure swarm eruptions of plateau or flood basalt type would be such as the Holothrain eruption a few years ago, and in historic times, Laki and Eldgjá. So, with that little bit of background into Iceland and volcanic systems in Iceland, why do we then want to ask this question? Why do we want to know what came first? Now, in the active zones, the neovolcanic zones, we only have a 2D view of the volcanics, because everything older is, or most things older, are buried. So what we see in volcanoes like, I'm going to start here in the top right and move anti-clockwise. We have volcanoes such as Askja, which it has been suggested is being cut by, or authors have found that the volcano is actually being cut by roughly northeast-southwest trending faults and fissures. And also in the northern North Volcanic Zone, we have Krafla volcano, which recent fissure eruptions have cut through the volcano itself. So in both of these cases, is this the fissure swarm that's coming up through the central volcano, or is it something else entirely? Then we're going to jump over here to the eastern volcanic zone. This is Katla volcano, just a Google Earth image. This is often cited as a mature central volcano with a single fissure, Eldgjá. And this is sometimes stated as being an embryonic fissure. So does that mean then that the fisher swarm is going to become more mature and take over the system? And equally, somewhere like Reykjanes, where we have mature fisher swarms, are we going to get a central volcano appear on top of that? It is also equally likely that in each of these places, something entirely different can happen because we have different crustal dynamics, different crustal thickness, different local tectonics, things like that. So, because we only have a 2D view in the neovolcanic zones, it's really useful to go out to somewhere like the East Fjords, where glaciation has cut through the volcanic strata and exposed central volcanoes and volcanic systems. Breiðdalur central volcano and dike swarm, the subaerial manifestation of a fisher swarm, is shown in this red box here, roughly in sort of the central part of the East Fjords. So the entire strata in the East Fjords is roughly all dipping to the west, which means that the eastern flank of Breiðdalur volcano is exposed. And you can see on this map there's neighbouring volcanoes, Þingmúli central volcano and dike swarm, Reyðarfjörður, Álftafjörður nearby. And we have some of the oldest central volcanoes here in the northeast, and they're young down to the southwest near Vatnajökull here. So, Breiðdalur itself, the volcano that was in the red box, that was previously mapped by George Walker and others in the 1950s and 60s. His map was produced in the 60s, and he classified parts of the central volcano and the volcanic system. And here's a simplified map, his simplified map that Thor is coloured in. And he describes a basaltic or mafic volcano flank, shown here and shown in this schematic image here. And at the head of the valley, he described the core of the volcano, which is an area of subsidence, which is infilled with what he described as agglomerate. And on top of that, we have what's called the volcano summit, which is rhyolitic, basaltic lavas and tuffs and sediments, which are roughly horizontal. Some more previous work. In 1993, Thomas Schnell did a PhD on the silicic magmatism at Breiðdalur, suggesting that assimilation fractional crystallization was the main cause for producing silicic magma at Breiðdalur. More recent work by Martin et al. 2010 had a differing opinion. They suggested through their work and their results that the silicic magma actually formed through partial melting. But they also dated, in a paper, Martin and Sigmarsson, 2011, the silicic magmatism from 9.1 to 9.3 million years. So throughout this project, obviously we undertook a lot of fieldwork out in the east, and then we put the results of this field mapping and also George Walker's map into GIS and digitized the map. The samples that we took throughout fieldwork were then taken to University of California, Santa Barbara for argon-argon age dating with Phil Gans. There were also some uranium-lead zircon age dates taken at the University of Tasmania, XRF at the University of Edinburgh, ICPOES here at the University of Iceland, as well as isotopic work through ICPOES, ICPMS, TIMS, here in Iceland and in Okayama, Japan. So, now on to the results. Paper 1 describes the geological mapping of Breiðdalur volcano. Obviously, it's a lot based on George Walker's previous work, which we've digitized along with some reassessments with more modern thinking of parts of the volcano. So this is the map. Obviously, it's rather complex for a PowerPoint slide, but I'm just pointing it out here. The map here on the left is actually out in the foyer, and here it is on the lovely Arctic DEM. Thanks, Joachim, for that. And the map here is on the Arctic DEM. And that's just there because it looks nice and pretty. So here is the simplified map. Again, this is very similar to George Walker's simplified map. And you can see the blue flank lavas spreading out here. This is the eastern flank of the volcano, and the western flank is presumably buried to the west. We actually redefine or separate the flank group into 4 separate groups. The 3 main groups I'll go through today. And these are described as B1, 2, 3, and northeast, essentially descriptive of their timing and where they are on the volcano. And I'll go through these in just a minute. Another thing we redefine is what George Walker called the core group. We define it as a caldera, and the black line here shows the approximate location of the proposed caldera fault. Walker actually did start alluding to this in later work, though in his actual Breitler paper he still called it the core group. So, early volcanism at the central volcano. That is typified, we've described it as being typical as what's shown in this image. Hopefully you can see that these are rather thin, very black lava flows. They're very, very different from the basement plateau basalts below the central volcano. These are thick, often over 5 meters, more like 15 to 20 meter thick. Grey, tholeiitic plateau basalts, and there's a group just below the central volcano known as the Grænavand porphyritic group. So just above that group, we have this very distinct change at this white line into these thin, black, mafic B1 group lavas. So, as the volcano continues to build, we appear to have an evolution of magmatism, and we get the first appearance of intermediate magmas, or intermediate lavas, of Icelandite composition. This is slightly higher up from the B1 group, which at its thickest is around 400 meters thick. And here we actually have a really nice example of one of the thick Icelandite flows. This is close to 30 meters, or around 30 meters thick. And Walker actually mapped this group as well, and we essentially keep the definition the same, but just rename it within our own groupings as being the B2 group, so lying above B1. Above the B2, so B2 is Icelandite lavas with some mafic lavas within it, is this plateau demonstrated here by this red line. And above this we have the B3 group, which has a morphology, or has lava morphologies very similar to the lower B1 group. So we go back into these thin, black, mafic lavas. Very different from what we see in the B2 group. So coeval with the upper part of this B3 group, we have the southeastern rhyolites, which is a group of rhyolites on the southeastern flank of the volcano. This is Flögutinde rhyolites, around 100 meters thick here. And this is coeval with the endpoint of the B3, and probably with what's described as the summit group that I'll go through in a minute. But next I'm going to the caldera. And this is because the caldera clearly cross-cuts the flank groups. And we describe this as, this disconformity between the flank group and the caldera as being a caldera fault. And that's shown here in this lower image down there. So we're up here in the head of Breitler, and we have the B2 and B3 flank lava groups, and here is the summit group, which I'm going to describe in a minute. And the B2 and 3 flank lavas are actually discontinuous around this red zone here. And it goes into this more massive complex of tuffs, sediments, and papilli-tuffs. So, within the caldera we have several different lithologies. There's actually basaltic, or very hydrothermally altered basaltic lavas that form the base of the caldera complex, and these are probably part of a plug which collapsed into the magma chamber during the initial caldera formation. Some lithologies, we have a lot of silicic tuff. You can see it here on this image that's being eroded away. And we have lapilli tuff, or what's called pumice breccia, which is what Walker called agglomerate. Lapilli tuff is a bit more descriptive of what it actually is. It's a fine-grained, ashy tuff matrix with lapilli-sized pumice clasts within it. And there's often clasts of basalt or rhyolite within different parts of this, this whole sequence within the lapilli tuff. And this image in the middle here actually shows a typical view in one of the gullies in the caldera. They are very easily eroded to scree, and this is another outcrop of lapilli tuff. Throughout the caldera, we also have a lot of intrusions. One intrusion is shown here. They often bring with them pyrite deposits, especially some of the larger ones. And some of the smaller intrusions are often actually very, very fine-grained, indicating that they probably intruded into rather shallow crust. There's also, interestingly, a lot of sediments shown here by siltstone. This siltstone is from a gully within the caldera that actually has trace fossils of some little wormy things that were crawling around within some form of a lake in the caldera lake, if you will. The entire sequence is characterized by highly variable dips. They often vary from one outcrop to another. And there's a lot of hydrothermal alteration throughout the entire sequence. Now, all of this suggests we probably had an initial explosive formation. It probably wasn't catastrophic, but it was certainly explosive, producing most of this lapilli tuff that we have infilling the caldera. And this formed a caldera that's around 8 to 10 kilometers wide and around 500 meters deep at its thickest point. We probably had a lot of nesting of calderas if the local changes in dip or anything to go by. And we certainly had shallow magma, whether it was short or long-lived, that's another question. But we certainly had enough heat to provide a good geothermal system in the area. Now, above the caldera group, we have a marked change into the summit group, which I've mentioned earlier. And this change is marked by change from very variable dips and dip directions in the caldera group, as well as a lot of hydrothermal alteration and intrusions, shown here by the kettle-nuclear andesite intrusion, into subhorizontal bedding with very little hydrothermal alteration outside of normal zeolite metamorphism. So the summit group is shown here above this black line here, and I'm just going to zoom in on that image there. So we have the lower summit group in the central area is comprised of tuffs, sediment, and some basaltic lava flows, as well as this mountain of Matahnúkur, which is a large, over-thickened, lava-like ignimbrite, probably deposited in a depression here because the rest of the ignimbrite thins out rather rapidly away from this mountain. PB just is plateau basalts, which are covering the volcano. Here you can see a thin section of Matahnúkur ignimbrite showing its rheomorphic flow texture, and in other places spherulitic texture with fiamme and often with welded pumices as well. Another part of the summit group over in the east is shown here in this log. We firstly have just above the caldera group, which is actually just down here, and the caldera fault is just off the image. We have a thick rhyolite lava flow followed by lapilli tuffs, composite lava, and a tuff bearing large clasts, and then a pillow breccia and pillow basalt, followed by basaltic lavas, and finally a very thick rhyolite lava flow of the Berufin fjallar rhyolite. So just to go into that sequence a little bit more, here is an image of this pelagonized silicic tuff in this sequence, and here you can see some clasts of granifier rhyolite, and actually in this sequence there's also gabbroic clasts within it. This image here shows the basaltic, or the mafic pillow breccia, where we have clasts of pillow basalts which are broken up and they sit within a matrix of pelagonized basaltic tuff. And this actually grades up into proper pillow basalt, suggesting we had a mafic lava flow flowing into some sort of standing water. Above this is the Berufjarðartinda rhyolite lava flow. This is a very, very large rhyolite lava flow forming the very, very top of the volcano. So as it stood proud from the landscape, this was probably the highest thing in the area. And this could be around 1 kilometer cubed in volume, so a very large rhyolitic eruption, with some error on that depending how much has been eroded away. This summit group is approximately coeval with some of the upper B3 group, which has been eroded away in this image, as well as with some of the southeastern rhyolites, one of which is shown here. And this is Flögutinda, which I showed in a few images back. So cross-cutting the entire volcano is the dike swarm, or parts of the dike swarm. This image here shows a typical field view of the flank of the volcano to the north of Breiðdalur. And you can see here these arrows point out some of the dikes in the dike swarm which are clearly cross-cutting the lava flows of the flank sequence in this image. This here is the map that George Walker made of the Breiðdalur dike swarm. The red ellipse here shows the main part of the dike swarm. I know it's kind of hard to orientate yourself on this, but here is Berufjarðar, and the main head of Breiðdalur is actually in here with the valley, just there. So burying the volcano are a series of plateau basalts. In the lowermost part, actually just off this image here, some of these plateau basalts appear to be intercalating with summit group lava flows. And in this image, which is in Uxi, in Berufjarðar, we can actually see lava flows which appear to be onlapping onto the central volcano itself. We have part of the caldera group, some summit lavas just above it, and the B3 group here. And we have a distinct change in dip with lava flows onlapping onto the volcano and burying the volcano. Just to go through that all again is this image again. Here we have, at the base, we have the B1 flank group. Then we go into the intermediate lavas and mafic lavas of the B2 group. And the last flank group is described as the B3 group with southeastern rhyolites coeval with the latter part of that. The caldera group cross-cuts everything, and the summit group is on top of this. So this is just a rock relations diagram to relate everything together. And here we have plateau basalts which cover the whole volcano. And this image actually shows all of that together in one, or most of that in one image. Paper 2 is based on this mapping, so that's why I took a while going through this first one. And it relates this mapping with age dating we undertook, argon and uranium-led age dating, in order to determine the age relationship between the dike swarm and the central volcano. So these are the flank group images that I showed. The lowermost sample that we have, or age that we have, is 10.1 million years plus or minus 0.2. This agrees very well with another age date from the Skessa Ignimbreit, or Skessa Tuff, of 10.15 million years, suggesting that the volcano started at around this time. We then have two age dates from the upper part of the B1 group, which are dated to 9.9 million years plus or minus 0.2. And that gives us a good age date for when we started to get more evolved magmas, intermediate magmas, erupting on the flank of the volcano. We then have an age from the B3 and summit group basaltic lavas of around 9.6 to 9.8 million years. However, these two samples both have a relatively large error of 0.5 million years. So we need to be a bit careful with these ages because of their very large errors. Now, the ages of silicic magmatism at the volcano all seem to be crammed towards the end of the central volcano's life. Two age dates from Martin et al. 2011 give an age of this intrusion and dome of Røyðarfell of 9.3 million years, and another intrusion over here to 9.1 million years, which agrees quite nicely with other age dates that we have, our youngest one being 9.1 million years from an intrusion, and some zircon, a group of zircons giving an age of 9.5 million years, which is just shown up here. Now, this age of 9.5 million years gives us an approximate age of when the caldera probably formed. Since this is our oldest silicic age date, we needed to have silicic magma have formed in order to form a caldera. And since this is the oldest date we have for silicic magma, that gives us probably a likely age of when the caldera formed. And the youngest date that we have for the whole of the central volcano is around 9.1 million years, which fits actually quite nicely with ages of the plateau lavas above it, above the volcano. So this image again shows an age that we have from actually slightly off this image of a plateau lava, giving around 9.5 million years plus or minus 0.4, so it has a bit of error in there, so it's got some leeway. But we clearly have onlapping of these plateau basalts whilst the volcano was still alive, as it were, was still active, until a group of olivine basalt lavas, which entirely cover the highest point, this rhyolite lava flow of the central volcano, by 9.1 million years plus or minus 0.2. So this suggests that the volcano was probably pretty much dead by 9.1 million years. The dike swarm is rather interesting. The oldest age date that we found for the dikes was 9.8 million years. So this is approximately, it's in some of the older parts of the central volcano sequence, but it certainly overlaps with the central volcano quite a lot. The youngest age date is 7.8 million years, and even with this relatively large error for this age, it still is a lot younger than the proposed death of the central volcano. And if we take this age as it is, then the youngest dike is 1.2 million years younger than the proposed burial even of the central volcano. And these dikes, many of these dikes are probably feeding plateau lavas which are onlapping onto and covering, burying the volcano itself. So just to go over all that again, here we have a box which shows the life of the central volcano, approximately 1 million years, from 10.1 to 9.1 million years. Silicic magmatism is crammed to the end of the life of the volcano from around 9.5 million years here. But the dike swarm clearly postdates the central volcano by up to 1.2 million years. Paper 3 was concerned with the geochemistry of the volcano and the volcanic system, and we wanted to tie this with the temporal evolution of the volcano. So this image is just to show the spread of data that we have. Most of our samples are basaltic lavas and dikes pushing up into basaltic icelandite. And then we have a bit of a gap here, and then the rest of them are mostly rhyolitic. This data set here is complemented with Schnell's data set, who was looking at the formation of the silicic magmas. So it has a few more samples of these intermediate magmas. But this image here shows clearly the gap we have between basaltic or mafic and silicic lavas and magmas. And this is matched with the field data that we have, where around 80% of the stratigraphy is mafic, around 15% is silicic, rhyolitic, and around 5% is this intermediate here. And that's important when I discuss the formation of silicic magmas in a second. So, because of time constraints, I want to just go through the stratigraphy of the volcano using geochemistry, essentially illustrated through this one slide. So the blue points here are central volcano lavas. The yellow points are thought to be plateau basalt lavas. And the orange points up at the top are actually the dike swarm lavas, just for reference. but I'm going to describe here the life of the volcano. And what we appear to have, using zircon to represent trace elements, magnesium to represent the evolution of the magmas, and titanium is also here for a similar reference, though it is more complicated because of how titanium interacts with oxides in tholeiitic magma trends. So pointing here mostly at MgO, we appear to have a progression upwards through B1 of lavas or more evolved basalts erupting up into basaltic Icelandite and the B2 group of Icelandite lava flows here in these ellipses. Interestingly, after this B2 group, we have a significant drop down into more, well, relatively evolved basalts, but becoming more primitive with stratigraphy. So this is the upper part of the volcano, the upper part of the B3 group, and these plateau basalts here are either part of the older part of the central volcano or part of the fissure swarm covering it. And shown on here is the silicic lavas, or silicic magmas, just for reference. So we clearly have some kind of a gap here where we have silicic magmas and relatively primitive magmas erupting here. And this, the geochemistry here is backed up with field observations of olivine basalts forming or erupting onto the top of these volcanoes. So just to conclude all that, Breiðdalur appears to be broadly tholeiitic, though it has some slight enrichment and incompatible elements. Now, the intermediate magmas appear to evolve, or have evolved, so potentially we have some fractional crystallization forming these intermediate magmas, but this seems to become less dominant in the silicic magmas because of this daily gap that we have and the sheer volume of silicic magma that we have. So we suggest, because of these, mainly the field examples, that partial melting probably formed most of the silicic magmas. So we agree with Martin et al.'s work from 2011. Also, the relatively primitive lavas that erupt above the central volcano, or towards the end of the central volcano, suggest perhaps that we have either an opening or a more permeable crust, allowing more primitive magmas up to the surface at this time. Obviously, that's still a bit of a question, but that is the potential. Now, we have a fourth paper within this thesis, but it doesn't fit entirely within the question that we have here for this talk, and due to time constraints, I'm just going to briefly go over it in this slide. So, we were concerned with looking at the isotopic geochemistry of Miocene East Fjord volcanic systems, including Breiðdalur. And this is basically because there was a bit of a gap in the scientific knowledge regarding this, where previously workers had suggested there was a temporal evolution due to plume pulsing throughout the East Fjords, but they had missed out some of the volcanic systems and not taken geology fully into account. So we originally wanted to assess the ability of isotopes to discriminate between volcanic systems in the East Fjords. And our results suggest that actually it's quite difficult to do that. Many of the volcanic systems are so similar in isotopic composition that you can't really discriminate between them, as you can with some volcanic systems in the current active zones. As shown here, this is a bit small for a presentation, but if you have questions about it, please ask at the end. Interestingly, our results from this suggested that the southernmost Álftafjörður volcanic system was more enriched in radiogenic isotopes than the rest of the Eastern Fjord volcanic systems, which actually, because Álftafjörður is approximately the same age as Breiðdalur and Þingmúli, we suggest that it's more of a spatial difference in the composition of these magmas rather than a temporal one. That's not to say there isn't a temporal evolution, but that we need to be aware that there's also a spatial one. So, I'm going to conclude the rest of the talk and the rest of the thesis essentially in a few slides. So, Breiðdalur volcano, the central volcano, initiated at around 10.1 million years. It erupted and built rather quickly, and intermediate magmas started erupting at around 9.9 million years ago. Silicic magmatism is entirely confined to the end stages of the volcano from around 9.5 million years ago, which is when we suggest that the caldera also formed. The volcano is then thought to have died at around 9.1 million years ago. And then the dike swarm continued after this for at least 1.2 million years, 1.2, 1.3 million years. So all of this suggests, or our evidence indicates, that the central volcano comes before the exposed dike swarm at Breiddalir, and that the fissure swarm, or dike swarm, is active long after the central volcano. So that essentially concludes everything. I just want to flash this up because I want to say thank you to, firstly, everyone for being here, and thank you to everyone that I've had the pleasure of meeting during my time moving to Iceland. These things aren't easy, so it's essential to have a good group of people around you to help with things. So, yeah, thank you to everyone. And the amount of people I've met in Iceland definitely isn't represented by all the people in these photos. But that's what Facebook gave me in the past week. So, yeah, thank you, and now I guess it hands over to the opponents.
So, well, thank you, Rob, for this very illuminating presentation. And you have to control this later. Yeah. So now it's the time for the opponents, and it is Professor Valentin Troll who's going to start, and the podium is over there so people can hear you. And some people don't quite have the stomach for what's going to happen now, but the rest of us will stay.
Thank you very much. So I guess we'll start. So thank you for the talk. It was most enjoyable. And fantastic field pictures. You must have been climbing quite a lot out there. So, but let's start with a general kind of question, with a big theme question if you're on mind. And I'm not sure there's a clear-cut answer, but I was wondering, this question about fissure swarm versus central volcano, which comes first? And there seems to be examples of systems where the fissure swarm is earlier, and then there's examples where the fissure swarm seems to be later. Your data seem to suggest the central volcano, it's almost coincident, it's almost the same time as the fissure swarm. Maybe it's a little older, but my big question is, how come that fissure swarms end up making central volcanoes? What is the defining reason why a fissure swarm might actually build a central volcano at a particular site, or why does the central volcano form at this place where it is?
Well, that's an interesting question. Why does the fissure swarm build a central volcano? Why does the central volcano form where it does on a fissure swarm?
Yes,
at a specific
what
site.
What is the criteria? I mean, and maybe there's no real answer to this, or maybe there's too many answers at this point, but I wanted to hear your opinion.
Yeah, so I think it probably deserves a broader discussion as well. And it's probably very difficult to answer, because we probably have to take each system at its, as I suggested earlier on, at its own merits. So with discussions that I've had with other people, including Thorvaldur, it appears that maybe at least in the northern volcanic zone, we appear to have fissure swarms and central volcanoes where actually the placement of the fissure swarm, or the entire system, is essentially controlled by the main rift, you know, this sort of main fracture through the crust. But the central volcano itself, why that's placed where it is, perhaps is due to some secondary tectonics, cross cross-cutting, such as we have in the north the Chernus fracture zone. And I think there's evidence for other fractures throughout the northern volcanic zone in an approximately northwest, southeast, if I get that right, trend. So where we have the meeting of these two, you probably have a focal point of magnetism. Also, I mean, it could be that these things form on the center of a Fisher swarm. Like, it appears to be that as you get further away from sort of the center of a system, you get less magmatism or less volcanism, as was shown by Auster, I think, and Paul, where Askja Fisher swarm isn't eruptive in the north, but is towards the south. So perhaps it's just that we have more magmatism here in the central part. And obviously I'm concentrating there on the northern volcanic zone because then in other parts it becomes rather complicated. For example, in Reykjanes, will we ever get a central volcano?
Yes.
I don't know. It's entirely plausible that we won't. And in the eastern volcanic zone, it appears, though it's obviously not entirely clear-cut, that we have the volcano there first before the Fisher swarm, but again, if there was a Fisher swarm, it's buried. And this is potentially due to the crustal dynamics in the area, the propagating rift sort of cutting through and maybe not allowing Fisher swarm style volcanism to come through, but rather more point volcanism has to come through, break through the crust there. So, an answer, I guess there's probably lots of different answers and a broad discussion to be had about it, and I don't know if there's a general consensus on these things.
I personally think there's none, and I'm not even sure we will ever find one. Maybe there is a broad scheme, but I think your point is quite valid that most of these systems, while they have some similarities, they might actually need to be addressed on an individual basis. So let me push on. Do you have any sense for why Breiðalur volcano is actually where it is? To be a bit more specific with kind of the same question.
You mean where it is in the East Fjords or?
Yes, along the fissure as well. And, do you have any indication, any structural indication why the volcano decided to build up just there?
Not clearly, though other workers have suggested, well, for one, why do the fjords and the valleys come down where they do? Some people have suggested, either in discussions or I think there's probably a couple of publications out there, that there are, again, these roughly east-west or northwest-southeast trending weaknesses or potentially faults that provide a weakness for glaciation, and so perhaps that's why we had the Breiðalur volcanic system and central volcano form at this point, where we had an interaction between the main rift and the smaller rift. There's an entirely different question as to where the volcanic systems of Breiðalur, Þingmúli and Álftafjörður, which are approximately coeval in time, where they actually formed on the volcanic zones or belts. Because, we have suggestions that they came from the northern volcanic zones. More recent suggestions indicate that they could have come from more towards the south, kind of around either the southern part of the northern volcanic zone or more like the eastern volcanic zone, or even something similar to the Öræfajökull volcanic belt, so this off-axis belt of volcanoes. The geochemistry doesn't 100% line up with that, but there are suggestions because it's slightly more, the volcanoes there are slightly more enriched. Perhaps we had this slightly off-rift volcanic systems that have then migrated to the northeast. So, well, firstly I want to ask, has that kind of answered, or can I go into more detail in that?
Well, I guess the simple answer is that you seem to be convinced that structures play a main role, and I think this is where people realize, not just here but elsewhere as well, that faults, and particular fault intersections, become more and more important in actually modulating volcanic activity, in locating it and modulating it in terms of the volume. And maybe it's also because I'm revising a paper right now where I like to propose that faults and volcanoes play together. So I'm particularly interested in that, and I think quite frequently, at least I have worked in the Scottish area of the North Atlantic, and there we see that fault intersections do seemingly play a role for several of the central volcanoes, where you have all the crustal structures and tertiary crustal structures, and the intersection of them might actually favor volcanic activity. So I believe it's going to be very hard for you to look under the volcano and really kind of find this out, but I think you're thinking along the right ways here. But let me push on a little bit with the overall scheme of things. The duration of activity on the central volcano, it seems a rather narrow window of about 1 million years that you have there. And intriguingly, this has been found in the late 90s for places like Skye, where Brian has worked a lot, and other volcanoes in the wider North Atlantic province. This 1 million year number seems a magic number that the volcanoes live for 1 million years. I've also done work in other places like the Canaries, and there volcanoes are alive for 20 million years. What's the reason for volcanoes in the North Atlantic being 1 million year volcanoes? Do you have an idea about that?
Let me close this one second.
Yes, please.
So this isn't shining on your face. I noticed that question. If it's going to stay closed. So why are central volcanoes why do they always seem to be around 1 million years?
In this part of the world, sir.
In this part of the world, yes. Well, again, that probably deserves wider discussion, but actually, one thing that makes things a little bit more difficult is that we appear to also have the life of the entire system, at least in this case, of being around 2.3 million years, approximately. So I sort of originally wanted to be thinking along the lines of perhaps the central volcano, perhaps the magmatism that is feeding the volcanic activity, because we're on a rift system both here and over in Scotland and Greenland, perhaps because of the movement, it maybe pushes away or pulls away the actual system away from the sort of magmatic input from the rift zone. So we would have a decrease in the amount of magmatism happening after around 1 million years. But we then have to tie that into the results that we have here of a volcanic system long outlasting the central volcano. But it at least seems, it should at least be fairly straightforward that because we're on a rift system and everything's migrating in Iceland, 1.9 centimeters per year.
Sure, I accept the rift argument, and I'm pretty convinced it plays a role, but what I'm still a little bit puzzled about is that you showed quite clearly that the Fisher swarm was active for a fair bit longer.
Yes, exactly.
How come that the magma coming up the Fisher swarm suddenly decided, I don't want to go to the central volcano anymore? How come in your view?
So it appears, my suggestion is that perhaps, the geochemistry broadly showed that, but also it's backed up by the field evidence of these primitive lavas, more primitive lavas, basaltic lavas erupting above the central volcano. So it seems to suggest that perhaps the volcanic system has become, for want of a better word, sort of too permeable to allow a crustal magma reservoir to either melt or, partially melt the crust surrounding it. There's the heat rather sort of comes through the crust too quickly so that it can't form these silicic magmas again or silicic reservoirs again. yeah, did I say that correctly? So the central volcano needs to build up with a relative point source, and the heat input from that then probably creates the silicic magmas. However, if we have continued heat input, then it may become that either the crust becomes too thin, or perhaps there's too many cracks or fissures. Some reason makes it slightly more permeable and allows more primitive magma up to the surface without actually ponding for too long a time in the crust, and therefore doesn't allow this sort of build-up of a magma reservoir and the more point source volcanism. Yeah, if that answers it.
That's
Okay.
surely a possibility. I don't think we can be sure about it right now.
No, exactly.
Another thought I had, and maybe that's no better than your view, is that once you actually build up a silicic volcano, imagine new fissure magma coming up, it's going to be increasingly hard for this magma to penetrate through the central volcano. And the taller the volcano, the longer the way up. And what we often see in systems like Teide volcano in Tenerife, it suddenly stopped having summit eruptions, and you get more eruptions in the periphery and along the rift zones.
Okay, yeah.
So it might still be the same kind of magma coming from depth, but suddenly it doesn't get stuck anymore within the central edifice. It might not have the time to differentiate, to fractionate, or it might simply, density grounds move to the sides to avoid this low density felsic edifice. And then, of course, it would also have less opportunity to melt the crust or to fractionate, depending on how you want to get to the silicic magma. So this is interesting considerations, and of course, we are all kind of in the process of learning more about them. I'm not saying there's a right answer, but there is interesting ideas, I think, and you certainly touched on some of them. So, Brian, do you have a question on this so far?
Yeah, first of all, I'd like to congratulate Rob on tackling a classic volcano. It's difficult to follow the footsteps of somebody like George Walker. Everybody will be watching what you do, obviously here to hear the results, and so I congratulate you on taking a project from literally starting in the field and taking it through to the laboratory. I think that's always a good education and in a very professional way. Talking about the location of the whole system, Val's first question is one that I was going to ask as well. So I wondered if geophysics, not you actually conducting geophysical work, but what geophysical data are available just in terms of magnetics, or just getting an indication of the crustal structure in general. Is there a database that we're able to
You mean
to help you?
sort of in the East Fjords?
Yeah, just for the whole area.
So as far as I know, it's at least the published data is relatively limited. If Brintis was here, maybe she could ask that a little better, or answer that a little better. But as far as I'm aware, at least, there isn't a good published data set. I have looked for these sorts of things, at least previous in my work.
View of the system, trying to sort of step back. Sometimes when you're working on something relatively small, seeing the big scale controls on it can be very difficult.
Can be tricky,
You're inside the forest and you can't really get anything, just a view of trees.
Yeah, exactly.
Which is not likely to be the case in Iceland. In systems where continental crust is involved, such as the Hebridean province in Scotland, certainly old crustal structures certainly seem to have a key role. And the sort of working model that people have, I think, accepted is that old crustal structures, where it's crossed by a fissure system caused by crustal extension, at that intersection, you just get a high magma flux. And that sort of pins the volcanic system. So in the Hebrides, for example, in Skye, you get the big central complexes developing essentially at the intersection or cross-cutting Caledonian age faults, Paleozoic fault, and the extensions system, which is essentially running north-south at that extension point. So I probably agree that can have a working model, but it's very difficult to pin down things.
Yeah.
In terms of the ages of the system, the error bars are large,
Mhm.
and I'm well aware of that.
Yes, exactly.
Every person that comes along to redate volcanic rocks always dismiss previous studies. They always sort of start off by saying, well, I can do better than that. But it is concerning that the errors that you've got are so relatively large.
Yeah.
Was magnetic data considered to see if there was any magnetic reversals within the interval of the whole system?
It wasn't considered in this project, but it is something that either would be interesting to do, though I think there's probably, there is previous work nearby where they undertook, a magnetic transit throughout the East Fjords. I'm not sure if the volcano itself has been done, at least published work, in detail anyway. I'm sure there's other people in the audience who might know better than that. But yeah, that would certainly allow us to at least tie things down a little better. But again, I've worked a little bit with magnetics as well recently, and that can also have a bit of difficulty with it as well, especially with such an age. But it would at least give like a relative age throughout the volcano and even of dikes within the system, I guess. So that would
Can I ask a question on the geochemistry?
Mhm.
Many years ago, I had an interest in geochemistry. I think I've probably fallen by the wayside with it. But with these dike swarms, did you look at the spatial relationships of the dikes in terms of their geochemistry, especially things like titanium zirconium ratios, where you can get an indication of the amount of melting involved to produce certain compositions,
Mhm.
and to see what temporal spatial relationships there are between the dike geochemistry and the overall evolution of the system.
So I kind of attempted to do that with dikes that are both from the north and from the south. Although I didn't look east-west. The issue is that, there didn't seem to be much of a difference. They're all very, very similar in geochemistry, and all of the geochemistries are rather hard to unravel from each other. And there didn't seem to be a huge difference to the north and south, but the areas that I actually took the transects are from two fjords that are approximately equidistant from the actual kind of center of the central volcano. So let's assume that perhaps the magma chemistry changes to the north and south, then I might not necessarily have seen that from where I took the transect. And actually, this is kind of a little bit why we went into the isotopic geochemistry of it, to see if there was any distinction between the dike swarm dikes either in the same system or from the neighbouring system of Þingmúli, which actually the dike swarm overlaps directly, or in parts directly, with the Breiðdal dike swarm. So these two things were clearly like right next to each other. And we kind of hoped that there would be some difference in geochemistry that might suggest that there was this spatial variation either along the Fisher swarm or at least between the two neighbouring Fisher swarms. And it essentially showed there wasn't. So my guess would be that there maybe isn't too much of a change from at least north to south that we could see. But I know that, in Iceland, I think even some of the longest dikes here may be up to around 30 kilometers long, maybe, which I know it's sort of significantly shorter than some other ones found in Scotland or down into the UK, where we have slight differences along the strike of them. But in short, I attempted something vaguely to that respect and didn't find any huge differences.
And again, magnetic fabrics might offer you some idea of which direction the relative vertically or horizontally material is. I know that that's fraught with its own
Problems.
own problems and arguments and issues.
Yeah, someone actually undertook a study of the Alftafjörður dikesform, which is another very well exposed dikesform. They undertook AMS, so.
And the results
I can't remember exactly what they found, unfortunately, but it was a while ago that I read that paper, so I'm not 100% sure what they said, and I don't want to sort of assume what they said.
Can I quickly jump in?
Yeah, please do.
I'd like to kind of follow up from this dike discussion a little bit. Now, if these volcanoes happen to form at the same time,
yes,
with the same chemistry, what would that tell us about the mantle?
Yeah. What indeed?
Yes. What do you think?
It clearly shows that we have a similar, a similar sort of zone or source zone below the central volcanoes, or the volcanic systems rather. Whether that's a single elongated deep magma reservoir where the mantle, magmas are going into and then kind of mixing along the length. I'm not sure about that, or whether it's just we happen to, because it's around 40 kilometers away as the crow flies from each volcano, and perhaps that's just close enough. There's also suggestions that the plume was slightly more active during the Neogene. So it could be that this played some role in sort of diluting some of the mixing that's in the deep crust or the asthenosphere. Presuming that that's where these melt signatures are coming from.
In your thesis, you're describing one volcano, I think it was to the south, that was a little different.
Yes.
And that was a little further away, but of the same age, and I got a little stuck when I read this, because my gut feeling was that you could possibly interpret this as a mantle inhomogeneity, that maybe there was a different type of mantle or a different mix of things available. I don't know exactly, I can't recall the distances, but let's assume this was, 50 to 100 kilometers or so, because that might actually tell you something about inhomogeneities in the mantle. If you want to accept that it's not maybe degrees of melting, which may not be the key factor here, then you have maybe made the start of actually mapping mantle inhomogeneities there. It's a very small start, but nevertheless, if you want to play this game further, there's quite some potential there.
Yeah, well, exactly. This was one of the interesting things that came from this study, and it was a little bit unexpected, to be honest.
Yes, I can see the aspect of being a bit, maybe even overwhelming at first.
Yeah, and certainly the isotopic geochemistry is it's easy to get very, very bogged down in different aspects, but it does seem to suggest that there is at least some sort of inhomogeneity between these systems, at least.
And then, of course, this has knock-on effects, because then temporal changes that have been described for late isotopes for the last, say, 10 million years or so, if you accept mantle inhomogeneities under Iceland, then what is actually temporal and what is spatial? And you're raising this point actually in your thesis. And of course, I guess you could have been a bit, I feel you could have been a bit more critical about some of these things in terms of the established models, but you rightly point out that there's quite some uncertainties that your data are actually implying for some of the existing large-scale models. And maybe that's not your task and not your job to clean this all up, but I think your work shows that there may be some fresh thinking required.
Yes.
And this, I think, is very important.
Yeah, this study was certainly meant to be a preliminary thing, and yeah, it would be really interesting to see if these ideas can continue.
I understand every PhD is only so and so long, and every funding source has a limit, so you cannot go beyond that. But this is, I guess, something that might be another PhD in the future for some other person, of course. So I would have a few more questions on isotopes with the felsic rocks, but do you have anything on this?
It's more the field relationships that I want to talk about, so please do finish your isotopic.
Good, then we'll do the isotopes.
Get out of the way.
Yeah.
I'm going to indulge in isotopes now.
I might need to intervene.
So, the question of how to make the felsic rocks in Breiðavík, it's a fascinating question, and it's one that I have been fascinated since my undergrad days, how to make felsic magmas. I still consider felsic magmas as the crown of magmatic evolution, and therefore I find it interesting how people want to make them. And I was intrigued by the Schnell data, because he or she, I don't know, that person seemed to have found more intermediate rocks than you had in your sample set. Do you have an explanation for this discrepancy? Because with the big compositional gap between the mafic and the felsics, I think your conclusion is quite substantiated. But, of course, the doubting question is, how come that Mr. or Mrs. Schnell actually found these other rocks?
Yeah, so, yeah, I guess I didn't mention it there, but because of the actual sort of starting question of this thesis, I wasn't actually concentrating on the intermediate magmas. I saw them in the field, and I maybe took a few samples here and there, but because we were looking at this relationship, but predominantly the relationship between the volcano itself and the fissure swarm, I was concentrating a lot more on the mafic sections and the silicic ones at the very top of the volcano. So I was a little bit less concerned with mapping those until it came to later on, after we had a bit more data, a bit more geochemistry, and obviously less time, that we started to just sort of see these differences. And I would have liked to have had more of these geochemical samples, and they certainly are there in the volcano. But the field mapping, at least I tried to be as accurate as possible when doing the field mapping with regards to what was intermediate, and also using some of George Walker's old work. So there's obviously some kind of error within the general percentages that I gave. So, but it still appears that there's less. However, without a much more detailed sampling, then we probably can't get the full picture without that very, very detailed sampling.
Texturally, are these intermediate rocks, is there anything that jumps out that makes you think that they could be just simply the product of mixing? They're just totally hybrid?
There's actually different intermediate magmas throughout the volcano. The ones that are on the flank, these large lava flows, appear to be, at least into a thin section, largely homogeneous. So there's no indications or no simple indication of mixing textures or anything like that in these flows on the flank, the ones that I've seen anyway. However, within places like the caldera and even on some of the summit groups, there is a clear indication that some of the intermediate magmas are formed, and even some dikes and sheets are formed through mixing. So it's either a dacitic or a rhyolitic mixed with a basalt or a basaltic isendite that creates the geochemistry, the whole rock geochemistry. I guess...
It's a thorough hybrid, it's not a mingled magma situation.
So in hand sample it would look like an andesite, I guess. But when you look in thin section, you start to perhaps see the differences. And I guess the real way to untangle that would be looking at the actual mineral chemistries, which is something that we didn't concentrate on in this project. I understand that, so it's actually Thomas Schnell that he undertook, at least in his thesis. And in some of the silicic feldspars, he does indicate that there's sort of oscillatory zoning in some of these, and I can't recall the ins and outs of all of the mineral geochemistry for this.
The intriguing situation that you describe with the felsic or silicic materials coming after the volcano was alive for something like 500,000 years,
yes.
Is that right?
Yeah.
So you have a mafic volcano that's building up, and then 500,000 years after, it's kind of it's a midlife crisis almost, given that it's only 1 million years. So and in that midlife crisis, suddenly it develops felsic rocks, and there's the isotopic work from Martin and your isotopes, of course. And I wonder, is there any indication from these isotopes what changed halfway through the volcano's lifetime to suddenly make it look very different and make it produce rather different kind of rocks?
Well, the simple answer might be, I don't know.
That's fair enough. But
yeah.
What ideas would you be able to develop?
Sorry?
What kind of models would you be able to develop? What would fit in that scheme?
In order to time when the felsic rocks were...
Maybe let me phrase it differently to help you a little bit. I guess I'm wondering, are the isotopes giving you any hint as to what was actually melted to complement the magmatic evolution?
Well, this is sort of mostly going off the previously published work. Our isotopes, we did sample some of the felsic rocks, but it's such a small data set that I can't base too much off it.
Fair enough.
But the previous work did suggest that, or at least Martin and Sigmason suggested that it was hydrated basaltic crust predominantly that was melting, rather than, for example, a lens of silicic rock that may have remelted or something like that. And this, I guess, the main way to undertake that, they looked at several volcanoes throughout the East Fjords and came up with a broad answer, whereas I've kind of, I think, tried to push a little bit in this, that we can't necessarily look at each volcanic system and say that's it for everything.
No, we can't. No.
So it would certainly need a more, and I think it has been done in other places, but a more focused isotopic work. For example, oxygen isotopes would be able to maybe discriminate this a little bit better, whether it's been hydrated crust or whether it's actually more primitive or not. Or,
it's very interesting, this problem, and of course I also don't know the answer for Breidelur, but there is several ocean island systems that seem to show this. For instance, in the Canary Islands, we on Gran Canaria as well as in Tenerife, these systems start off basaltic and they go basaltic or mafic, let's call it that, for quite some time, many million years. And at some point they change to felsic volcanism with large ignimbrites and all that kind of thing. And it's been always a puzzle, how come? And one suggestion out there that I personally find quite attractive is that you may have had an episode where your mafic magma supply was waning a little bit. And that could have actually caused magma to pond at shallow levels. If that happens, you have more time to interact with the country road and things like that. As long as you flush the system with mafic magma, there's little room, and some people argue this is why we get so few felsics on Hawaii, because it's a very productive system. We're flushing it all the time. There's no magma that's stagnating and has time to kind of evolve and things like that. And maybe that's what you're seeing there. I wonder.
That's an interesting concept.
Your volcano might have had a little bit of a a holiday there.
Yeah,
and,
calm down a
in
little.
that time, the magma that didn't quite get pushed out could have resided somewhere in the, I don't know, top 5 or 10 kilometers and could have done something else. And intriguingly, I also think that in the Hebrides, what we often find is that felsic volcanism comes right at the start of the volcano.
Yeah.
But there we have continental crust. So I think if it's easily melted, it might actually produce felsic volcanism right early. But I think in the basaltic upper crust of Iceland, it might be more difficult. So this is just the thinking, and again, I don't know the answers, but from comparing it to other systems, there might be some lessons to be learned. And I said it also in my report that I think one of the aspects that might allow you to kind of push the models a little bit further is actually by taking other information and trying to integrate this a little, and maybe for your publications, something in the discussions where you also would widen the validity of your work a little bit, put it on a broader footing, and of course, other people might cite it then a little more.
Yeah, this is certainly some valuable feedback there.
So I guess I'll leave the isotopes there.
Good. Can I just ask a general question? Obviously, I'm interested in field relationships of the different units that you've got. So first of all, the nature of the caldera margin. It doesn't look as if it's particularly well exposed. Would that be a fair way of describing it?
That would be. Yeah.
And can you say anything more, just to give a sense of what
So,
observations you made?
Well, the images that I showed, I'll just describe it so I won't flick through all the images. But the images that I showed where we have this margin, it's kind of a very broad zone.
It's more like by inference.
Yeah, it's kind of like where you can see that there's a lava flow there, but it's not over there. On this, the southern side of the Breitdaler Valley itself, there's a large landslide which has come down and covered where we're inferring the fault to actually be. But there's actually another area which I have an image of. I didn't have time to go through it. To the south, no, it's behind you now, but there's actually a view where you can't exactly put your finger on it because there's a river running down which is clearly following a weakness. But on one side, to the east, we have these thin black central volcano lavas which kind of connect with the rest of the flank group. But then on the other side, we have clearly silicic material. In this image here, it's actually, the upper part is a rhyolite lava flow which has a relatively shallow dip, so it's probably part of the summit group. However, where the photo is actually taken from, I don't have a photo of it here, but there's tuffs, lapilli tuff, some very strangely altered, I think it's a basaltic lava, but it looks very strange. And these are all very steeply dipping, around 50 degrees to the southwest. And that's kind of essentially where I'm stood when I took this photo here. So we have within, I think it's, well, there's a sheep for scale there. So we have, at least several meters, tens of meters, this contact where it is, so it's relatively sharp. It's obviously not something we can quite put our finger on, unfortunately. So the exposure in eastern Iceland is obviously really good compared to some other places, but it's not quite good enough to do that.
The other contact that you would like to put your finger on is the base of some of these sequences. And again, you showed in some of the general images a line on the images indicating where it was. Was that a bit of a disappointment in terms of what you could actually see, whether what you had weathering profiles at the top of some of the sequences before it changed to something completely different?
Yes, in some ways. There was, in some areas, there's actually a sequence at where we propose the base of the volcano is, which is kind of close to where Walker suggested it, or essentially similar to what Walker suggested as well. And we have this change from the plateau basalts to the thinner lavas. There doesn't appear to be much of an erosional profile, but it's been proposed that during this time we probably had more or less an Arctic desert environment. Very little standing water. It just went through. So little weathering, but in some gullies, although I'm not sure how extensive it was, it didn't appear to be particularly extensive. There was a rather thick, approximately 2 meter thick, sedimentary horizon that didn't appear erosive. It was very fine-grained, so sandstone that appeared, it was kind of in this zone, but it's a small outcrop. I'm not sure how pervasive, how far it went in the stratigraphy, so I'm not sure if this is really an indicator of anything. So I didn't particularly express anything about it because it's difficult to say whether it is actually something or not. And I think, this is something rather disappointing about some of these East Fjord volcanics, because they formed in probably a slightly warmer environment, and any water just permeated straight through and didn't stay on the ground, except for in certain cases where you had like a caldera or something. But it's certainly nothing like these huge erosional contacts that you can get in Scotland and things, which are really cool.
Can I quickly ask you about the caldera margin
Yes.
a little further, if that's okay? Do you have any indication about the orientation of this presumed caldera fault, or is it completely undulous to you?
The exposures that we have, if you link them up, it gives a roughly north-south kind of trend. But because of where the exposures are and because of the dip, we would expect it to be the eastern side that we see. So we're sort of maybe seeing this approximate, I don't know which way my hand's supposed to be facing. This approximate sort of curve, the northern orientated curve of the fault. This is assuming that it's circular. That's an assumption, just based on other calderas around the world and in Iceland. But with regards to, do you mean also the dip of the fault?
I was wondering about the dip because you have drawn your caldera faults, and of course it's speculative, but you've drawn them inward dipping. And I've seen this quite frequently. Icelandic researchers seem to like the inward dipping. And of course the problem is that this is what caldera researchers in the classic sense, and we know that from experiment, would call the space problem.
Yes.
You're actually not getting this thing down if you're drawing them inward dipping, unless you have rifting at the same time.
Yeah.
So this is why in sediments, for example, people see, without any tectonic influence that is, they see outward dipping, bell jar-shaped fractures, because that allows the caldera piston to actually go down into the magma system. If you do it this way, your piston gets stuck.
Yeah, exactly.
And you need to actually have tectonics, and I was wondering whether your sketch is implying whether rifting was actually part of the caldera formation, or whether this is just coincidence because you looked at some other sketches.
I'll firstly go into what we see in the field. At least in that, the view here towards the north, the line, as I say, it's a zone. The line probably isn't exactly the right place, but it almost appears like it's a stepped margin, and it does appear like it's kind of dipping to the west, but it's really poorly exposed, and that is probably because this thing will have been subaerial, and there'll have been erosion on it, which is also indicated by some sort of sandstones and larger breccias or conglomerates that we get within the caldera and even in the summit group. So we probably had some mass movements, I'll say, on the caldera, which caused it to be inward dipping on the surface. However, under the surface, I would say actually my sketches are probably influenced by these other ones, because in my head I actually do think about the outward dipping.
That's my gut feeling as well, because if you look at some of the classic work by people like Pete Lippmann or so, who studied calderas all their lives almost, they define this near surface erosional margin, where you oversteepened caldera walls may actually start to crumble, erode in, and they define this near surface shape of a caldera, which then grades into these outward dipping falls at depth. And you get this intriguing shape of kind of inward movement, and then the outward falls underneath. And I was merely interested whether you had given it some thought, but you clearly did.
Yes.
But maybe the influence of some previous workers was very intense.
Yes, that probably is unfortunately the case. But yes, and we clearly, we obviously don't have
you don't
that
have
exposure,
but I think you understand the problem I'm pointing out.
Yes,
so.
I do.
How much erosion has taken place? Do you have
We have a rough estimate because of zeolites that at least in the upper part, let's say of this image here, we have probably around 500 meters to a kilometer of material gone. So when you're in the valley floor, it's more like it's over a kilometer. In some areas, it's probably around 2 kilometers as well. And that's kind of very similar around much of the East Fjords as well. This erosional depth up to maximum of around 2 kilometers. But on the surfaces, we have relatively low-grade zeolite alteration. Some of them aren't altered at all, though. Actually, these sequences here show a few low-grade zeolites. So it's probably a few hundred meters, perhaps to a kilometer, that's missing actually off the top. Yeah.
The other intriguing features that you'd have anticipated might be present based upon, again, work in the Hebrides, are cone sheets. And clearly, when cone sheets were first identified, there was this expectation that systems such as you have described may well have similar sorts of intrusions. Clearly, they don't. There was no fracture patterns within the rocks that hint at the same stress fields that might have allowed cone sheet geometries where man was able to cause essentially uplift of the crust as emplacement took place. There's no indication of that stress field.
Well, we have, I don't think I have an image of it, but we have one mountain, which is essentially just an enormous cliff. And it has what could be described as cone sheets. They're sheets anyway. They have some sort of angle of dip to them, around 40, 45 degrees, something like that. That is indicative of a sort of cone sheet, but it's only really exposed in this one area, and it's on one mountain, and so it's like it's tenuous. I could suggest that perhaps there was, but it's not solid, and I think that's also, even if it was present, is partially due to the erosion of the east-west valleys, and because of the geometry of the volcano that we can see, it just may not be as well exposed as we might want if we were looking for that. But there are indicators that there are probably some sheets, but calling it a swarm might be
and there's no radial dike distribution. Everything is essentially one trend.
It mostly seems to be, yes. It's very, actually, other than silicic dikes, more felsic dikes, they can have many different orientations actually. And but otherwise, there doesn't appear to be this radial. I mean, it could be something that might need more work, more concentration, and it might not be Breitdalur volcano that's actually the best one to go to for that. Because there is other work in Geti, I think, to the south. I think it was Steffi Burkhardt who worked on it. Perhaps you were an author on that as well. Where they found sheet swarms, I think it was.
I think
can't remember.
you're almost looking at somewhat the wrong level for that.
Yeah.
I think you
Perhaps.
almost want to be a little deeper for that,
Yeah.
because this would potentially be under the canal.
Mm.
So
Yeah, well,
at
yeah.
least the Gatorfell system is in the Gabbro kind of.
Yeah, it's perhaps the level of intrusion that we're seeing is too much controlled by maybe more regional fractures or something like that. I'm not really sure. I can't.
As a sort of
It's just
preliminary to juniors field work, obviously the big difference between you doing this study now and George Walker in the sort of late 50s is that satellite images were not available to him to be able to just do sort of fraction analysis, trendology
Yeah.
on what you see. Did you feel that gave you any advantage before you went into the field to just take the bigger picture?
Yeah, a little bit. Yeah, certainly. He obviously went in the long way around, and was looking at it with sort of fresh eyes, new eyes, and it certainly does help having these images. So actually, when I started the aerial imagery of the East, having come from the UK, where even Google imagery was far better than the aerial imagery that was available, but now the aerial imagery is actually very, very good, and you can sit at home almost and trace these lava flows almost.
Is that since you started your PhD?
It's actually improved. Yeah, I think there was perhaps maybe Joachim's gone, but he might know. I think they published some in 2017 or something like that, which were updated from slightly older. I mean, it was still better than what George Walker had, but they certainly weren't perfect things. You could see approximate contacts and things like that. But when you have a distinct change in lithologies, that's really easy to see on aerial imagery, and you can go through. And I think, obviously, the next thing is having much more 3D imagery. And one thing I would love to do, and we're probably, Birgir here works a lot on that, is photogrammetry of the area. So actually either taking a flight or, as you were talking about earlier, drones, where you have these, so you can put them into a 3D mesh and essentially map sat at a desk. Yeah.
Yeah, I think the 3D thing, I think I mentioned in the report, I think you have some great opportunities there, should you wish to go there.
Yeah.
Great, I have one final question, if that's okay.
Yes.
And it's an intriguing question. You have worked on a volcano that a legend like George Walker has worked on.
Yeah.
So, did you find that George Walker was wrong with something? Maybe not, but did you detect something where he kind of got it wrong in your view?
Actually, I wouldn't say got it wrong.
Mm-hmm.
There are things like what he called the core complex, where I think more modern views suggest it is a caldera. But actually, as I mentioned in the talk, he actually, in discussions with other people, started suggesting that rather than core, he might call it caldera. I think this was work in the 60s or something like that. So, yeah, there's little things like that. There's perhaps bits that I saw in mapping that he didn't see, but largely, I don't think so. But that, but also, I guess, I use this as background, and there's a lot of things where, even though I'm trying to be critical, it's still like, this is pretty iconic work, and clearly a lot of work has gone into it. And I don't usually try to put too much on interpretation either. So things that he saw, essentially no. I wouldn't say that I think he got anything particularly wrong. Just
So
perhaps we would
what you're
describe
saying is he did a
things.
fantastic job for his time. Is that kind of how I understand?
Yeah, definitely.
Okay.
I mean, the only other things we've done is made some contacts a bit more accurate, quite a bit more accurate, because we can use GPS and aerial imagery, where he was just using a general map and feel. So I wouldn't.
That's great.
Yeah.
Fair enough. Thank you.
Thanks for the questions. Thank you.
Pleasure.
All right.
I have no further questions. I saw that one of your field assistants in the middle of your picture, bit of a giveaway. What is your field assistant, the collie dog?
Yeah. Pippin. She's very important.
Yeah.
She's often a scale. It's a good scale.
Part in the centre of the picture, I think that must tell the audience your opinion of.
Yeah. Even, my partner Kate, she's like, wow, Pippin's in the middle, what? So,
It wasn't just me spotting it.
yeah, exactly. Yeah, I saw Velvet's face light up as well when she saw a picture of Pippin. So, yeah.
Anyway, in summing up, I would like to congratulate you on being brave enough to tackle an area that people will go and look at, people will take your map out, people will walk over the sections, and they will, in a way, judge what you've done. It's very easy to study a volcano in the middle of nowhere, the Andes, that you'd be confident people will never visit. But you've done something that's mainstream and yet screaming out for a modern interpretation. And so here we are, 70 years later, or 60 odd years later, and you've tackled it with a great enthusiasm. You've had a good eye to detail, and I congratulate you on your work and hope that you publish this so that it will encourage further work and for people to go and look for themselves.
All right. Thank you.
Well, this concludes the examination of the candidate by the opponents, and thank you, Brian and Valentin. Now, if there's anyone who has a question or possibly two short questions, now is the time to ask. And the usual suspects are here, so Ingi.
I'm sorry if you didn't submit your question. No, I'm joking. Come on. Yeah, I'm very happy to discuss anything as well, especially if we.
May I follow up a little bit on the dip of the caldera fault? So the opponent was saying it might dip in shallow and then dip out deeper. What is the original depth of where you have mapped the caldera fault?
So, originally it would have, the entire caldera will have been at most 500 meters deep. That's the thickest section we have. The exposure of the largest exposure that we have, even though it's relatively poor, is actually probably around the same amount. It's so in this image here, the pink rhyolite, which hopefully you can see there, the bottom of that, the dotted line, the horizontal dotted line, is around 600 meters high. So we have a rough exposure from about 600 meters to the base of the valley at about 100 meters above sea level. So again, like an exposure roughly of 500 meters. If that is that.
So the original crustal depth is only 500 meters?
In at least in this area, although it was probably buried with plateau basalts and everything like that, up to 1 kilometer, probably at this area. Is that correct? Is that what you were asking here?
Is there any sign of buried
No, that's an interesting question. I wouldn't say so for Breiðdalur and Þingmúli. There's no clear indicator anyway. They are slightly more enriched in incompatible elements, which on, for example, a lead-leg graph would suggest they're pushing up into more enriched mantle EM sort of zones, lead-lead zones. But perhaps the argument could be put forth for Álftafjörður to the south, because that shows more similar geochemistries to the Öræfajökull volcanic belt, which authors have suggested that there is a sliver of, or good evidence for, I might say reasonable evidence for continental crust beneath there. But I wouldn't be able to place anything strongly. I wouldn't be able to say strongly, though if someone was interested in taking this further, then it perhaps shows that there's something you could look for. Though I never, I'm not exactly sure if it does. It's difficult.
Okay.
So Iceland was at least the western and eastern fjord were quite a bit closer, or maybe not fjords, 10 million years ago. Did you compare Breiðdalur to geochemistry of central and west fjords?
In where, sorry?
In the west fjords.
Yes, I did a little bit. But there's actually, there's relatively little recent work on a lot of the volcanoes in the east, and a lot of the areas in the East Fjords that's published anyway. But geochemically, the West Fjords appears to have a much broader range, much broader range than the geochemistries that you find in the East Fjords. I'll just, because it's easy to do, I'm just going to quickly jump to this slide showing the lead data. So on the left here, these grey circles show the East Fjord array, which was done by Kitagawa in 2008, or in his PhD in 2006. So it's a really good data set of all the plateau basalts in the East Fjords. But even that doesn't quite have the range in values that the West Fjords has, suggesting that there's almost definitely, well, not almost definitely, but there's probably something different, slightly different happening in each of these areas. And, I mean, we do have a relatively complex architecture of the rift zones, obviously in the neovolcanic zones. And it's probably just reflecting this, I would have thought. But in short, yes, I did try and do some comparisons, but didn't find anything particularly solid to work from or work towards. Okay?
Yeah. Okay.
Those dikes, the new ones that may have formed then million years after the volcano potentially died, did you notice any different chemical composition as in they were more
At Breiðdalur, no. We didn't appear to find a change, well, not a notable one, temporarily. But interestingly, though, this youngest dike actually has a very different strike to the a slightly different strike to the rest of them. It's actually sort of northeast, southwest trending, where the others are pretty much north-south. So it is slightly different, but it clearly is. It's at least in the same area and is mapped as the same swarm. And we also have another ever so slightly older dike, which is definitely from the Breiðdalur dike swarm. But this 7.8 million year one is at least causing rifting at the Breiðdalur fissure swarm area. But geochemically, there doesn't appear to be a particular temporal change within the dikes. They're all rather disappointingly similar to each other. Yeah. However, I think there has been a study on the afterfjörðardægsform geochemistries, which still needs to be published, I think, but that showed some interesting changes, didn't it, Kate? So.
Okay. Well, I think this concludes this session now. So now I ask the opponents to come with me, and we consider the outcome, and the rest of you don't go anywhere.
How do we stay here? Remember to do this. Okay. Am I allowed to step off the podium?
Check what we need to say, or whether it is just an appropriate thing to say. Okay, thanks. Okay, yeah, yeah.
Some important things have been discovered. Okay.
Would you like me to put the lights?
It's fine. Nobody's taking pictures. Okay. The following text has been documented and signed into the PhD registry of the Faculty of Earth Sciences. Doctorate from the Faculty of Earth Sciences, Robert Alexander Askew, 17th of January 2020. By resolution of the Faculty of Earth Sciences, Robert Alexander Askew's dissertation, Breiðdalur Volcanic System, What Came First, the Central Volcano or the Fisher Swarm, has been approved for a doctoral defense in geology. The defense has been made, heard, and accepted. We therefore declare you, Robert Alexander Askew, a doctor in geology, philosophy of doctor from the University of Iceland. In confirmation of this award, I want you to stand up to present to you this certificate of PhD. It's not just, and it's in 3 languages, as you probably know, so you can practice your Latin last night. So, and this is the supplement. We're not going to read that. Congratulations.
Thank you.
Okay. Maybe the opponents want to say a word or two at the end.
If I'd known the certificate was also in Latin, I would have suggested that perhaps we conducted the whole exercise in Latin. But too late now. We'll need to do that maybe next time round. Anyway, my congratulations with you. I've always been an advocate for the field-based project and see where it takes you. I think you've done an excellent job. More projects like this, more research of this type, I think, increases our understanding of these systems. And congratulations on what you've done.
Yeah, so congratulations from my side as well. And I enjoyed the work you did, I enjoyed the thesis, I enjoyed the defense. I have to admit that I guess we realized both that there is some questions that still require answers, but good research often raises more questions than it solves. So I think this is a positive aspect. And what I particularly enjoyed is the respectful way in which you treated previous work. That's not always the case. A lot of people go out to disprove the people that were before them, and they built on weaknesses other people had. And you did not actually do that. You built your work on your own observations. And this, I believe, has a lot of merit, and I'd like to kind of give you credit for that, in addition to the work you did. So, good job. Well done.
Okay, Rob, would you like to some famous final word here on this podium?
Oh dear. I've been talking for so long. I already showed it my thanks slide, so you all get one thank you. No, but thank you very much to everyone for being here. And again, thank you so much for coming across. Thanks for reading the thesis. And
that was tough, actually.
I know. And thanks for enlightening questions. And especially thanks as well, again, to Thor, Ármann, and Phil's now gone to sleep. But thank you all for everything throughout the years here at the university, for all of the opportunities that have been granted to me, including getting to poke some active lava, which was very nice. So. Okay.
Well, thank you. Well, I want to thank the candidate for his presentation and for the answers to the opponent's questions. Also, especially want to thank the 2 distinguished opponents to take the time to come here. It's a very important job that you do in making sure that the highest degree awarded in science is done on merit, and that's what good opponents do. So thanks for doing that. And Dr. Robert Alexander Askew, the Faculty of Earth Sciences, wants you to learn more about Iceland. So we present you with this book on Iceland. It has pictures of Iceland. Well, Iceland is this place where you have been now for the last 2 years and where you are working now. So I hope this will be a nice book to have and show perhaps to other people. So congratulations.
Thank you very much. Thanks.
Okay, and I want to say that this is not over. And the opportunity to speak Latin is still to come. Because we go to Askja, where there is a ceremony, and people are free to speak in Latin as they wish. That being said, I say that this ceremony is over, and thank you all for being here today. Thank you. Okay. Well, I've shaken your hand. This is good. This is good.
Thank you. I'm gonna.
This is an opportunity to have two people really concentrating on your work.
I know. Yeah, it's been very, very good. I don't need to say that anymore. Let's just. Sorry. Just gonna sign that out. There we go.
Do you need help with anything?
No, I don't think so.
Here's a printed copy of your thesis.
Yes, yeah.
And you can do as little or as much as you want. I have no requisites, no demands on it. I've got to say that the fourth word was wrong. It should be fiction, not what.
Been away from.
I explain when, choice of two, you use which. But that's neither here nor there. I'm a pedant. You can burn that if you wish.
After that comment, you might.
Yeah, I mean, it's a rather peculiar thing.
People will download your thesis, that's for sure. I don't know how it works in here, but you know, with the internet.